So, students, in our last lectures, we have completed the following topics: phenomena of refraction of light, types of, and these subtopics: types of medium, terms related to refraction, laws of refraction, and important cases. Okay. Then also we have completed this topic, apparent depth, and we derived the formula for both the cases for apparent depth and normal shift for both the cases when the object is in denser medium and when the object is in a rarer medium. Okay. Now in this lecture we will see that what is total internal reflection and what is a critical angle, what is the formula for a critical angle. Okay, so let's see. So total internal reflection. So to understand the total internal reflection, let's see this diagram. So let's say this is an interface, and for this interface here is a medium. That medium is a denser medium. Okay, this medium is a denser medium, and absolute refractive index for this denser medium is mu d. Okay, then above medium is a rarer medium. This one is a rarer medium, and absolute refractive index for this rarer medium is mu r. Okay, now I am taking three cases. You can see here all these three cases. So if like we know what is the Snell's law. Okay, we already studied about the Snell's law. So Snell's law said that sin I by sin r, the ratio of sin I by sin r is constant. So by this I can say that sin I is proportional to sin r. Also I can say that I is proportional to r. Okay. So by the Snell's law, you can see that I is proportional to r. If you increase the I angle of incidence, the angle of refraction will also increase. Okay. So let's see these cases one by one. So this is my first case or the first ray diagram. So this is a normal, and let's say there is a light ray. It is the light ray is coming in this way. Okay, by this way, and this is the incident ray. This is the angle of incidence. Okay. Now here, this is the denser medium. This one is a rarer medium. So light ray is traveling from denser medium to rarer medium, and we now very well know that when the light ray travels from denser medium to rarer medium, it goes away from the normal. Okay, we know that from our previous lectures that this light ray will goes away from the normal like this it goes away from the normal. Okay, and this angle is called angle of refraction. Now by this relation I is proportional to r. Okay, I am just increase, let this point is a. Okay, so I am increasing the value I, and I am increasing the value of I like angle of incidence such that this R becomes 90 degree. Okay, see here. Okay, so I am increasing the value of I. Okay, so this is my incident ray, and this angle is I. So I am increasing this angle I such that the angle of refraction, this is the refracted ray, and this is angle of refraction. This angle of refraction becomes 90 degree. Okay, so that value of angle of incidence at which the angle of refraction becomes 90 degree, that angle is called critical angle. Understand this thing? Okay, the the value of angle of incidence, the value of angle of incidence at which the value of angle of refraction becomes 90 degree. Okay, that value of angle of incidence is called critical angle, or that angle is called critical angle. Okay, so now you understand what is the critical angle. Critical angle is an angle. Okay, critical angle is an angle at which the angle of refraction becomes 90 degrees. So you can see here, so this angle is called critical angle. Okay, this angle is called critical angle. Now let's see what happens if I increase the value of angle of incidence more than the critical angle. Okay, let's see here. what happens? So again, let's say this is a incident ray. This is my incident ray. Now here I just increase the value of I more than critical angle. Okay, this I is more than critical angle. Then what happens? We know that I is proportional to R. So if the angle of incidence is more than critical angle, then this light ray will comes back into the same medium. This light ray comes back into a same medium like this. This light ray comes back into a same medium like this, and this phenomena is called total internal reflection. Okay, and that in short it is called TIR. TIR, total internal reflection. Okay, now again I am just again, let's see all these three diagrams. By the Snell's law, we know that the ratio of sin I by sin R is constant. So I can say sin I is proportional to sin R. So if sin I is proportional to sin R, then I is also proportional to R. So in this case, this is my angle of incidence. So this is the angle of refraction. Now this light ray is going from denser medium to rarer medium. So it bends away from the normal. So it is also a very important point that the TIR is only happens when the light ray travels from denser medium to rarer medium. When a light ray travels from medium to rarer medium, in that case only it goes away from the normal and there will be a chance of a TIR. Okay, so this is very important point you have to remember. Now what happens when I start increasing the value of I, angle of incidence, I am start increasing so that the R will also increases. So when the R becomes 90 degree, so when the R becomes 90 degree, the angle of incidence is called critical angle. Okay, this I is called IC. IC is what? Critical angle. So critical angle is the angle of incidence at which the refracted angle becomes 90 degree. If I further increases the value of angle of incidence more than the critical angle, then what happens? This light ray comes, this refracted ray will comes back into the same medium, and that is called reflection. And that kind of reflection is called total internal reflection. So I hope you understand the concept of total internal reflection. Now let's derive the formula for the critical angle. Okay, so I can apply the Snell's law here. So by Snell's law. Okay, by Snell's law. So here light ray in this diagram, from this diagram I'm saying. So here the light ray is going from denser medium to rarer medium. So denser medium to rarer medium, I can write mu RD, uh, relative refractive index of rarer medium with respect to denser medium. So it will be equal to mu R by mu D. Okay, and it will be equal to sin R from this first diagram. Okay, ray diagram. Now from second, if R is equal to 90 degree. If R is equal to 90 degree, then I will be equal to IC. Okay, I already explained you. So if R is equal to 90 degree, then I is equal to IC. So I can write as mu R divided by mu D is equal to sine IC divided by sine 90 degree. Okay, and from here I can write sine IC is equal to mu R divided by mu D, and that sine 90 will equal to 1. This sine 90 is 1. Okay, so sine IC is equal to mu R by mu D. Okay, and now from here I can write for critical angle IC is equal to sine inverse mu R by mu D. Okay, mu R by mu D. So this is the formula for critical angle. Let's see a case where, let's say, rarer medium is air. So if rarer medium is air, so its value is 1, and the denser medium is having refractive index mu. So in this case, I can write the critical angle IC is equal to sine inverse 1 upon mu, because there are number of problems given where the interface is of glass and air. Okay, so you can apply this formula. So this is the formula for the critical angle. Okay, so I hope you understand the concept of TIR and the formula for critical angle. This is the formula for critical angle. Okay.